Hi there, I'm Hao, and it is just another video of me solving random code problem. So let's begin. Today we have the serialize and the deserialize binary search tree. So basically, we are being asked to write a function to convert a actual binary search tree into a string, and then we have to also deserialize it from a string back to a binary search tree in the exact order, right? And the encoded string should be as compact as possible. So how could we do this? So we can look at the example. So 6, 4, 10, 3, 5, and 11. Just no, right? So how would we start this? So I think we can use either pre-order traversal or post-order traversal to store this because it would be easier for us to locate the node, right? If we use the in-order traversal, um, it will be a little bit more difficult to locate the root node. So we can like go left as far as possible when we store um our value of the tree, right? And we can separate them by comma, so we can split it up into an array later. So 5, 10. So pre-order is we have to process the root first, right? So the root always the first one, and then the left, and then the right, right? Post order is pretty similar. It's just left, right, and then root would be processed at the end. Okay. Um, and then no, and then 11. Right. So basically we can just ignore the no here because the binary search tree is not guaranteed to be a complete binary tree. So if we have like a huge tree, if it is skewed, then we're gonna have a lot of we're gonna have to allocate a lot more space for the node here, right? And the solution want us to be as compact as possible. So we actually like don't need to store the node, just the value. So if we can locate the root, right, we can figure it out the children accordingly. So this is our result, right? Resulting string after we serialize it. So how would we deserialize this? So we can like iterate to the input string, right? We can split them into an array, right? Where each of them will be um each element will be split in between the comma, right? You can just split the string by the comma and get the array, and we can process it. So we want to uh say this is 6, right? The first element is always the root node, right? And we have to go left and go right. So whatever on the left side would be smaller than the root, right? So 4, 3, and 5. And whatever on the right would be greater than the root. So 10 and 11, right? And we just keep going, right? The first one will always be the root, and whatever's on the left will be smaller, and on the right is bigger, right? Same here, 10. It is an empty array, and it is 11, right? So what is our base case? Our base case is when we only have one or zero element left, right? So if it is an empty array, we can just return no, right? Because there isn't any children left. And if it is only one element, then we can just return the node, right? The new node, right? Like this, and then we can return back up, right? So 6 dot left, right, equal to the subtree. So we just like return the parent uh, backup, right? Same for here, right? So this solution works, but um, as you can see, we have to spend extra space to store the left and the right children, right? The left and the right array for the value smaller and greater than the root node. And not only that, we also need to spend extra time to sort, not sort, but like to filter out the value smaller or bigger than the root node at each recursion level, right? And that is not ideal. So in fact, there's an easier way to do this. If we can just use two pointer, we can have an upper and a lower bound, right? So let's say we have like an a pointer for the index here. Let me change the color. So let's say it is our index, right? So we always start by creating the parent, right? And then as we iterating down, instead of having an array of future value, we can just give it a bar, right? We can start out by uh, infinity to infinity, right? And then as we iterating left, instead of filter out an array with the value smaller than the root, we can set the upper bound, right? So the lower bound will be the same because we are going left, right? And everything is smaller, but the upper bound is 6, right? Nothing can be greater than 6, right? And if you go right, we change the lower bound, right? 6 to infinity, right? So everything on the right side has to be greater than 6, right? And everything on the left side have to be smaller than 6. So this is our bound, right? And we're gonna iterate to the left side first, right? Because we serialize the tree using the pre-order traversal. So we always go left as much as possible, right? Before looking at the right side. So every time we go down a level, we will increment the index. Okay, so the index now is pointing at 4, right? So we just create a new element at 4, right? And we keep going. So as we iterating down, right? We're gonna have a new bound, upper bound. Upper bound now is 4, right? And we just keep updating our index in 3. We go left as much as possible, right? And we keep going down. So our new bound now is 3, right? Next negative infinity to 3. And now as we go down, we just keep incrementing, right? So now 5, if you look at 5 here, we will realize that 5 is actually shouldn't go here, right? Because 5 is greater than 3. So if it is not in between this bound, right? It is invalid. So I can just return no, right? Because 5 is greater than 3. Okay. So now when I return back up, because I go left as much as possible, so then I return back up, I have to look on the right, right? So on the right here, what is our bound for the right? So our lower bound would be 3, right? It has to be greater than 3 and smaller than 4, right? Our new bound here, everything has to be greater than 3, right? Because it's on the right side and smaller than 4 because it is in the left of 3 or 4. And then 5 is not doesn't fit into this bound, right? 5 is greater than 4. So we can just go ahead and return no, right? So we are done. We return back up. We finish with the left subtree here, right? So now we look at the right side here. 4, what is our bound here? Our bound is 4 and 6, right? 4 and 6. And 5 is between 4 and 6. So 5 is in here. And then we update our pointer and we go to the next level, right? So our next level, our new bound would be, it is our upper bound, right? Lower bound would be 4. 4 and 5, right? And 10 is greater than, it's not in the bound, so we return no. Sample here, our bound will be 5 and then 6, right? And 10 is not in the bound of 5 and 6, so we just return no, right? And then now we are done with this left subtree, right? Now we look at the right side, our bound will be 6 and infinity, right? 10 is in between 6 and infinity, so 10 goes here, right? and then I update our pointer as I move to the next level, right? So our new val is 6 and 10, right? 6 and 10. So 11 is not in between 6 and 10, so we return null. It's the left side, so we'll look at the right side. Our new val will be 6, sorry, 10 is the lowest, 10 to infinity, right? And 11 is in between this val. We add 10, right? Sorry, 11 is in between 10 and infinity. So we add 11 here, right? And then we update our pointer and we keep going down, right? And now, because we are out of bound, we can just go ahead and return null, right? We finish the left side, we look at the right side, it's bound, so we return null. So what is our base case here? So our first base case is when the index pointer is out of bound, right? That's number one. The second thing is when the value at the root, right? The value at the, no, sorry, the value at the pointer is out of bound, right? If it is on the left side and it is greater than it is greater than the max, the upper bound, or it is lower than the um lower bound, right? Then it is invalid. So we just return null. So using it this way, we don't have to create extra space every recursion level. Okay. So let's go ahead and code this up. So for the root, okay, we can iterate through. We can create our BFS hyper function here. We can look at the left, the right, right? And we always process the root first, right? So we can do reverse the push all at val. We only want the value, right? We need our array here. And we have to call our BFS function passing in the root, right? And we can return the root the the- um, so we start from the root. We push in the root dot val, look at the left as much as we can before we look at the right, right? Okay. And I think that's pretty much it for Serialize. Okay, let's move on to Serialize. Okay, so what do we have to do here? Oh yes, I forgot a base case. So if R is null, right? We don't want to process it. If R is null, we want to return it. Yeah. So that is an edge case that we think about. Okay. Okay, so how would we deserialize this? Um, so let's create our hyperfunction as usual. So as we discussed earlier, we're gonna have a lower bound and upper bound, right? So I can call this low and high. We can start from negative infinity to infinity, right? Infinity. Okay. And I can so remember our data after the serialization is a string, right? So now if we want to change back to an array, we need to do the split, right? So data the split by the comma because we joined by the comma earlier, right? Okay. And we also need to create our index, right? Starting from 0. Okay. So what are our base case? So if the index, right, the node at the index, the node is our array of values here, right? If the uh, index is out of bound, so index is equal to data dot length. Oh, sorry, node dot length. We want to return no. This is the first case. Or if it is out of bound, right? Which means the node at index is less than the lower bound, right? or the nodes at index is greater than the upper bound, then we want to return null, right? This is our base case. Okay, yeah, and we want to process the parent first, right? And then we want to return the parent at the end, right? And then we want to look keep iterating to the tree, left first and then right. So parent dot left equal to the DFS of low. So our low would be the same, right? But our high would be the upper bound, would be the parents of routing, right? So similarly for the right side, the right, um, the upper bound stay the same, but the lower bound become the parent of value, right? So we create the parent, we set the parent dot left to whatever being returned here, right? Which is either null or a new tree node. Okay, let's give it a try. Oh, one thing we forgot to do beside this error is that we have to also increment our index every time we uh, go down a level, right? So let me do that. Okay. Oh, so we start from negative infinity to infinity. So when we go down a level, we set the upper bound for the left and we set the lower bound for the right side. Okay, we split the data, we start from index 0, we increase the index every time we go down a level. Our base case will correct. So let's look at this. Okay, this is also another edge case. So if it is an empty string, right? If we split something on an empty string, it would be an array of something like this, right? So we need to also check for that. So if the data is equal to an empty string, then we don't want to process that. We don't want to split. We don't want to call the DFS. We just want to return null, right? Because an empty tree would be just be null. Okay, and it worked. Submit. Okay. Uh, what's wrong here? Is that because I had to check this explicitly? No. Nope. Loss of index. Oh, right. Another mistake that I make that we also have to think about carefully every time we serialize and deserialize something is that remember initially our tree node, right, have the integer value, but when we turn it into a string, it is no longer an integer, right? So whenever we want to compare, we need to turn them back into an integer. So I did that by using a plus sign here in JavaScript, which means converted in the string into an integer. And now it worked. So thank you for watching.